Okay, let's continue with the binary eutectic phase diagram for limited solid solution. But before that, I want to recap about what we have learned from binary phase diagram before. Okay, so we have learned about the isomorphous phase diagram. And isomorphous phase diagram ni is a complete solid solution. Okay, and remember it can only exist in liquid phase or or solid phase, and the intermediate of both phases, which is alpha plus liquid phase or solid plus liquid. And remember that it can only exist in one solid solution. For example, alpha only. For binary eutectic phase diagram for non-solid solution, okay, the phase diagram will look like this, and then it can have more than one solid. For example, in this phase diagram, solid A and solid B. Okay, so it has phase liquid, solid A plus solid B, and it can also exist in liquid plus solid A and liquid plus solid B. And remember that for eutectic phase diagram, it will have a eutectic point, where eutectic point 2 is the composition of a mixture that has the lowest melting point. So in other words, eutectic point ni, okay, is where the material, okay, or the component can exist in three phases. Okay, so if you look at here, it can exist in liquid, and it can also exist in solid A plus solid B. Okay, so today we are going to look at for the binary limited solid solution. So the limited solid solution is where the components are completely soluble in liquid state, but it has limited solubility in the solid state. Okay, it meaning that it is soluble in liquid state, but however in solid state it has a limit. Okay, and usually the phase diagram will look like something like this one. Okay, if you look at closely, it looks like the same as your eutectic no solid solution, but it has solubility. So where is the solubility line? So later on we will see that. Okay, so if you look at here, okay, it has solid A and solid B, and then this one is A, E, and B. AE and EB is the liquidus line. So meaning that above the liquidus line, okay, it exists in liquid phase. And then we have AC, CD, okay, and BD. Okay, so below this line will be all liquid, all solid. So this one will be the solidus line. And then we have CF. Okay, this is where the limited solid solution phase diagram differ than the non-solid solution phase diagram. So we have CF and DG here. So DF and DG here is referring to the solvers line. Okay, and what is the solvers here? Solvers CF, okay, is referring to the solubility limit of B in A. Okay, so meaning that this one is A, and then you will have to mix B in A. So this is CF here is the maximum concentration of B that you have to add in A, while DG here is shows the solubility limit of A in B. So this one is B, so meaning that maximum of A that you can add in B is here. This is the limit, okay, because this is limited solid solution. So remember, this is where the both of his phase diagram, eutectic phase diagram, differ. Okay, for example, copper argentum phase diagram, or copper and silver. So we have the eutectic point. Okay, and then remember this one is the solvers. Okay, this one is copper, so meaning that this one is maximum, the limit of argentum that you can add in copper, where this one is the limit of the copper that you can add in argentum. Okay, and then this one is Tm here is referring to the melting temperature of copper, and this one is the melting temperature of argentum. So if you still remember, melting temperature is also equal to freezing temperature. Okay, and then this one is the eutectic point or triple point, where three phases can exist together. Three phases exist. And then below the eutectic temperature, it will form two different solid phases, which is alpha and beta. Okay, so this is where the determination of phase and phase composition, and also the wake fraction. This is similar as what we have learned from previous lecture, which is rule number 1, rule number 2, and rule number 3. And then rule number 3, we have to apply lever rule. Okay, coming down to the before that, okay, for the limited solid solution, okay, because it has a eutectic point here, so remember the similar as what we have learned from non-solid solution, it will also have hypo and hyper eutectic region. So to the left of your eutectic point will be hypo eutectic. So hypo eutectic will be counted from here until your eutectic point. And then for the hyper eutectic, it is located to the right of your eutectic point. So it will be from the eutectic until here. Okay, it must be counted just before the solver's line. Okay. Okay, so for example, the copper argentum system, okay, three single phase regions. We have L, okay, we have liquid, and then we have alpha, and we have beta, okay, and then we also have the intermediate of them, which is liquid plus alpha, and liquid of beta, and also alpha plus beta. So we don't see this alpha only and beta only in no solid solution phase diagram. This one, there is no solver's line, so therefore there is no solid B only, solid A only, no. Okay, for no solid solution. But for limited solid solution, we have this single phase of solid. Okay, TE limited solubility. So for alpha mostly copper, okay, and beta mostly nickel. Okay, this one is clearly from here because this one is 0% argentum, so this one will be 100% copper. So at alpha, it will consist of mostly copper, and in here 100% argentum, so it will consist mostly nickel. For eutectic temperature, no liquid below eutectic temperature. Okay, this one all exists in solid. Okay, 100% solid. And the CE here is referring to the minimum melting temperature composition. And the eutectic reaction will be like this one, liquid into alpha plus beta. If you want to see this you can see this very clearly from the phase diagram. This is the eutectic point. So it is liquid turning into alpha plus beta, and this reaction is reversible. It can also become alpha into alpha plus beta into liquid. Okay, so that is why the reaction is like this one. Okay, so let's do the first exercise. So this is, if you get this kind of phase diagram, okay, you can see the solvers here. So if it has a solver, so remember it will become limited solid solution. Okay, then label each phase region X and Y. So this one is liquid. Okay, and then we have here beta, and then this one we have alpha plus liquid. Okay, so what will be the phase here? Okay, so this one X is located in between of beta and liquid, so it will become liquid plus beta. And then for Y, okay, it is located below the solver's line and solidus line, so it will become all solid. So what kind of solid here? Okay, this one we have beta plus liquid, and this one is alpha plus liquid, and we have the eutectic point here. So remember, liquid eutectic reaction is liquid turning into alpha plus beta. So Y will be alpha plus beta, or beta plus alpha. Okay, so in this case, because beta is located to the right and alpha is located to the beta is located to the left and alpha is to the right, so we have to make it beta plus alpha. Okay, you need to follow whatever from the phase diagram. And then this one, the composition is consists of Sn and Bi. Okay, I forget about the chemical name, so I just denote it as Sn and Bi only. Okay, so determine the melting temperature for pure Sn and pure Bi. So where is this Sn? Sn is beta. Okay, so where is the melting temperature? The melting temperature will be here. Okay, so the melting temperature for Sn will be 232 degrees Celsius. And for the Bi is located here. And the melting temperature or freezing temperature, which is also is the maximum temperature in the phase diagram. Okay, melting temperature will be the maximum or the highest temperature in your phase diagram. Okay, so the Bi melting temperature will be 271 degrees Celsius. So determine the eutectic temperature and eutectic composition. So eutectic is located here. So the eutectic temperature will be equal to let's see, 139 degrees Celsius. So this one, if you were to answer in your examination, okay, remember it will have plus minus, so you can put 140. Okay, if you see it as 140, you can write down is 140, but it cannot become 120 because it too far from the from the correct answer. And then the composition will be 57% of Bi. Okay, and for the eutectic cooling curve, okay, it will behave the similar as the pure metal, where it will have the flat line here, the constant temperature for solidification. Okay, let's look at the next example. This one is lead and Sn, PbN Sn. So for 40% of Sn, alloy at 150 degrees Celsius, find the phases present. Okay, so 150, 40 weight percent of Sn and 150. So the point is here in the red one. Okay, so what are the phase present? There are two phase present, which is alpha plus beta. And then this one, remember, this one is coming from your rule number 1. And then the composition of the phases, this one is rule number 2. Okay, so for rule number 2, okay, so now we want to find the what is the composition of alpha and the composition of beta. So remember, what you need to do is you have to do in rule number 2, we have to do a tie line. Tie line where you need to extend the line until it find alpha and extend another line until it find beta. Okay, and then extend it down to find the composition. So this one for alpha, C alpha, okay, we can answer it as 10 weight percent of Sn. And for the beta, we can answer it as maybe 98 weight percent of Sn. So let's look at the answer. Okay, almost similar lah. Okay, 10 or 11, okay, it's good enough. Okay, because we have a plus minus range. And then find the relative amounts of each phase. So this one is rule number 3, where you need to apply level rule. So remember, in level rule, we have to label it as, let's say this one is R and this one is S. So if we were to find the weight of the alpha, so it will become, we have to take the S, the beta. So S over S plus R. And if we were to find beta, so it will become R over R plus S. We have to take this one. So S, what is S? S is the length of this one. So just now we note this one, we take it as 98. And this one is 40. So 98 minus, sorry, I write it down here. WA alpha will be equal to S over S plus R. So it will become 98 minus 40 over 98 minus 40 plus R. What is R here? This one is 40 and this one I take it as 10. So 40 minus 10. Okay. And then for beta, it will become R over S plus R. So R is 40 minus 0, 40 minus 10 over 98 minus 40 plus 40 minus 10. Okay, so the answer will be 97% for alpha and 33 weight percent for beta. Okay, and then let's look at the next exercise. Okay, so this one, this phase diagram, it doesn't look very much like what we have learned in the from the first slide here, but this one is no limit solution phase diagram because we have solvers. We cannot say this one is no solid solution, and of course this one is not a complete isomorphous phase diagram. Okay, so state the type of binary phase diagram here. Okay, so if you do not understand, you will say that this one is not in your syllabus, but this one is in your syllabus. Okay, remember, so this one will be the binary limited solid solution phase diagram, or binary eutectic limited solid solution. This is the correct answer. Eutectic limited solid solution. If you say binary eutectic phase diagram, it doesn't answer the question. Okay, it must have no solid solution or limited solid solution or isomorphous. Okay, so next, identify the melting temperature of pure aluminium and pure silicon. So where is this aluminium in silicon? So let's look at the composition down here. This one is aluminium and this one is silicon. Okay, so meaning that this one will be 100% aluminium or 0% silicon. And this one will be 100% silicon or 0% aluminium. Okay, so this one will be your value of silicon temperature. If you want to find the temperature, you have to look at the pure one. So 100% silicon. Here, this one is 100% aluminium. So the melting temperature is the highest or maximum temperature in your phase diagram. Okay, so for aluminium, pure aluminium, which is located here, the maximum or melting temperature will be 659.7, and for pure silicon, the maximum or the melting temperature will be 1414 degrees Celsius. Okay, for this one, compute the weight fraction of each phases for an alloy containing 40 weight% of silicon. 40 weight%. So this one is 100% silicon. So this will be 40 weight% of silicon at temperature slightly above 577 degrees Celsius. So 577 is here, where this is the eutectic temperature. So it want the above eutectic point. So maybe somewhere here. And 40 degrees Celsius. So this is the value that we want. Okay, so similar as what we have learned before. Okay, first of all, we need to apply rule number 1. Even though it doesn't state you have to, even though it only want you to find weight fraction, but when you want to find the rule, this one is coming from rule number 3, but you have to apply from rule number 1, because it is easier for you if you follow the rule number 1, 2, and then only you can answer rule number 3. So rule number 1, what are the phases present there? Okay, now we have this one is liquid. So what is the phases at A? Okay, so this is a very tricky question, because it doesn't write down the phases at A and B. Okay, so it's actually at A, it will be, so if you look at closely here, A and B is not a name of the solid or name of the liquid. It is a unknown phase A and unknown phase B. Then it is already told here that this one is liquid. Okay, the other one is understandable. And we have here liquid alpha, and liquid beta somewhere here. Okay, so what will be the phases at A? This one will be, so if this one alpha, this one is in the middle of liquid and alpha, so it will be alpha at L plus alpha liquid plus alpha. And then at A is located between L and beta, so it will be L plus beta. And unknown phase B will be alpha plus beta. Okay, so if we want this is where we want the point just now. Okay, above the eutectic point. So rule number 1, what are the phase present? The phase present will be L plus beta. Then rule number 2, what are the composition of L and beta? So we want to find Cl and C beta. So remember, what we have to do is we have to apply tie line. So extend the line from the point until you find L, solidus line, and then extend it down, and then for this one, extend until you find beta. So Cl will be maybe it is told here that it is 12.6. So I think 12.6 is located at the eutectic point. So I want it to be 13, maybe 13. It doesn't matter because like I told you, it will have a range, okay, plus minus. So, and for beta will be 100 weight percent silicon. Then only we can answer the weight fraction from rule number 3. So WL and W beta. So WL, okay, S, this one is R and this one is S. So WL, we have to take S over S plus R, and W beta will be R over S plus R. So S will be 100 minus 40 over, okay, this one, length of this one is 100 minus 40 over 100 minus 40 plus R will be 40 minus 13. Just now I take it as 13. 40 minus 13. And for this one, 40 minus 13 over 100 minus 40 plus 40 minus 13. And then the answer will be, okay, 68%. So I hope you can try to calculate by yourself, okay. This one will be 69% and this one will be 31%. Okay. Then let's look at the microstructure. Okay. So consider the composition of lower than 2 weight percent of Sn. Okay. So you will have a complete phase diagram. Okay. But then this one is they only we are only referring for composition of below than 2 weight percent of Sn. So 2 weight percent is here, this one, and then let's see what are the composition exist here. So at here it will consist 100% liquid, hijau, the green one here, and then here, okay, now this one is liquid plus alpha. So the liquid, it still has liquid, then the nucleus of alpha will be started to form, okay, and then here, okay, it will become only alpha solid. So it has formed the grain, the grains has been formed, okay, no liquid left. And then for this one, consider the composition between 2 weight percent until 13.3. Okay, so it's located here. Okay, so here the only phases present are liquid, so it only has liquid. And then here this one is L plus alpha, so it has liquid but the nucleus of alpha will be started to form. And then here we have the alpha. Okay, this one we have alpha only. Okay, and then it is completely solid alpha. The blue one, complete solid alpha. But then here, this one is alpha plus beta. Solid alpha plus beta. So what happened is, okay, this is where the beta, okay, the solid alpha will be mixing or will be joined by the solid beta, little bit of solid beta. Okay, but the primary structure there will be the solid alpha. Okay, And then consider for at the eutectic point. This one is eutectic composition, which is 61.9. Okay, at 61.9 here. Okay, so above here, this one will be all liquid. And then here, okay, at eutectic region, it will be in lamella form. Remember? Okay, lamella form, alternating layers of beta and alpha. Okay, so you can see the beta one, which is the blue one, and the alpha is the blue one, and the red one is the beta. Okay, the beta and alpha will be in alternating layers, so it will become belang-belang macam tu lah. Okay, and then consider between 18.3 until 61.9. So 61.9 here, where it is the eutectic point. So 13.3 from here until your eutectic point, this one is where the hypoeutectic region. Remember, hypoeutectic region. Okay, so for hypoeutectic region, so let's see what are the phases present. Above here, it will become all solid. And then here, it will become liquid and the formation of nucleus alpha, blue one. Okay, and then above the eutectic point, you see this one is eutectic. This one is above eutectic point. Above eutectic point. Above eutectic point, okay, it is still alpha plus liquid, okay. But below the eutectic point, okay, okay, the lamella formation too is already exists because it is happening after the eutectic. Okay, this one eutectic, the alternating layer has been formed. And then after the eutectic point, below the eutectic temperature, okay, below the eutectic temperature, okay, this one is below eutectic temperature. The alternating layer from the eutectic region, the eutectic point stay. And then because it is hypoeutectic, okay, it will, the bulat-bulat ni akan ada. Where the bulat-bulat ni nama dia adalah pro-eutectic alpha ataupun primary alpha, ataupun saya suka guna pro-eutectic alpha. Okay, pro-eutectic alpha tu maksudnya anak dia lagi lah, anak alpha tu. Okay, dekat hypoeutectic, this one is happening at the hypoeutectic region. Okay, tengok hypoeutectic, ada liquid, we have liquid, and then liquid with primary grains of alpha, this one, liquid with primary grain of alpha, this one is liquid. And then we have two-phase solid, which is, we have eutectic alpha, eutectic beta, with primary grains of alpha. Okay, with primary grain of alpha. This one lah. Okay, so this one boleh tengok balik dekat dalam nota if you were to confuse bila nak jawab soalan nanti. And then, okay, this one is hypereutectic because it is located after the eutectic composition. Okay, consider 61.9, so this one is eutectic composition. Until 97.8%. So, sampai sini. Sampai sini. Okay. Remember this one is, we name it as hypereutectic region. Hypereutectic region. So let's see what are the phases exist. So atas ni it will all exist only liquid. Okay, liquid. And then here, this one is where the L plus beta phase. Okay, it will consist of liquid with primary grains of beta, primary grains. Okay, primary ni maksudnya macam anak-anak dia lagi lah. Okay, the nucleus of beta has been formed and it is only primary je lah kat sini. And then below the eutectic temperature, yang ni bawah ni is below the eutectic temperature. Okay, it consists of two-phase solid with primary grains of beta. So it consists eutectic alpha, eutectic beta, sebab this one is coming from eutectic tadilah, dia dah jadi eutectic, so dia akan jadi alternating layers ni, tapi dia akan ada bulat-bulat ni pula, but now bulat-bulat ni adalah pro-eutectic beta, bukannya alpha, beta, warna merah. Okay, so boleh tengok clearly kat sini, this one is biru. Okay, this one is merah. Biru is referring to the alpha and merah is beta. Okay, so if we were to look at in the microscope, macam ni lah rupa dia. At the hypoeutectic region, okay, this is the eutectic lamella form ni, and then we have a grain of alpha, primary ataupun pro-eutectic alpha, bulat-bulat ni. And then at the eutectic region, eutectic point, dia akan ada alternating layers. There is no primary grains. Okay, and then for hypereutectic, okay, we have the pro-eutectic beta. Okay, so this is the difference between the hypo and hypereutectic microstructure. Okay, so now let's look at the invariant equilibrium. So dah nak habis dah. Invariant equilibrium ni, okay, this is where the different system have different types of Alloy transformation. Okay, so invariant equilibrium involve three phases coexist in, maksudnya dia akan ada three phase dekat satu point. At one point, it has three phase. Okay, it exists only at one temperature. Okay, one point and one temperature. And then the three phases ni dia compose at the point, one point tu lah. Okay, and it has 0 degree of freedom. So below are the example of Alloy transformation at invariant equilibrium. Okay, so we have eutectic, macam yang kita belajar eutectic tu, that one is considered as invariant equilibrium lah. Eutectic, eutectoid, peritectic, peritectoid, metatectic, monotectic, sintetik. Tapi yang awak akan biasa jumpa adalah yang empat ni. Empat ni kena ingat dan biasakan. Ingat apa? Just remember the reaction. Contohnya macam eutectic. Eutectic is, dia punya reaction dia adalah from liquid turning into alpha plus beta, or solid. Okay, kalau L into A plus B, so this one is also eutectic lah, sebab this one is referring to solid, So what about the eutectoid, peritectic dan sebagainya? Okay, so if eutectoid, okay, it is from solid become another two solid. Okay, from gamma turning into another two solid, alpha and beta. So for peritectic, it is liquid plus alpha. Okay, phase liquid plus alpha. Okay, example here, a liquid turning into alpha and beta. So this one is eutectic point. Okay, eutectic reaction. Then from one solid into another, it become another two solid. So this one is eutectoid. And then liquid plus alpha, liquid plus solid, it turning into another solid. This one is peritectic. And then two solid, it become another solid, another one solid. It is terbalik dengan eutectoid tadi. So now two solid becomes another one solid phase. Okay, so macam mana kita nak buat, macam mana soalan kalau dia tanya pasal invariant ni? Okay, let's see this one. Figure shows an incomplete copper and zinc phase diagram. So this one is not the phase diagram that we have learned just now. Tapi soalan ni dia boleh tanya kalau dia nak tanya pasal invariant points lah. Okay, so let's look at the what is X and Y. Where is Y? Y here. Okay, so let's look at X here. What is X? So tengok what kind of invariant points yang ada dekat sini. Kalau tengok kat sini, this one is we have solid plus liquid, and then dia berjadi apa? Okay, so solid plus liquid, kalau peritectic solid plus liquid, it become another solid. Okay, so gamma, this one is we have gamma. Okay, and then this one we have gamma, and then this one liquid, and then we have delta. And then this one we have another delta. Okay, so what is missing here? So we have, maksudnya X ni will become delta lah. Okay, so this one is peritectic reaction. L plus solid, it becomes another solid. Tapi solid apa? So tengok gamma ni dah ada. Sini pun dah ada gamma. Sini delta, sini dah ada delta. So apa yang tak ada kat sini? Kat sini kita tak ada delta. Betul tak? Delta. Okay, X will become delta. And then how about Y? So Y akan jadi, so kita padam dulu. This one is delta. Okay, so delta ni akan jadi apa? So kita tengok. Okay. So kalau kat sini dia boleh jadi satu lagi reaction, which is delta into dia jadi dua solid lain. Okay, this one solid, then dia jadi dua solid lain. Okay, satu solid jadi dua solid lain. So dia boleh jadi Eutectic. Okay, so this one off. So kat sini kita ada delta, sini kita ada E. Okay, so kat sini boleh jadi apa? Kat sini boleh jadi delta plus E. E saya tak tahu nak sebut apa benda ni. Epsilon, E lah. E. Okay, so dia macam tu. Kalau nak cari the regions dia ni, awak kena tahu cari dia punya invariant points, dan awak cari yang berdekatan sebelah-sebelah dia tu, apa yang tak ada. So dia akan jadi yang tu lah. So find invariant points. So what is the invariant points? So let's see how many invariant points kita ada. Kat sini kita ada peritectic. Tadi, that is why I know this one is delta. Okay, this is the reaction here. And then we have, furthermore, we have eutectoid. Here we have eutectoid. Okay, kalau nak tahu invariant pointnya dekat mana, biasa dia akan ada dekat bucu. Kalau tengok ada bucu-bucu macam ni, ni ada, ini ada, ni lah ada invariant points. And then we have peritectic reaction. Okay, so this one is, I think it won't be very difficult, because okay, now you are in online, you don't have to memorize this one. So let's say this question is being asked in your final exam, you can refer to your note untuk cari dia punya reaction. Okay, kalau face to face punya final exam, then you have to memorize this one lah. Okay, identify A and B. So let's say, what is A? A. Okay, so kat sini kita ada beta plus gamma. Dekat sini ada gamma plus L. Dan sini pun gamma plus L. So gamma. So beta. So kat A ni akan jadi gamma lah. Okay, tekan so the B tu ada apa pula? B ni, this one is L, this one is beta plus gamma. So kat sini akan jadi beta plus L. Okay. Okay, and then describe the phase transformation for invariance point. So how many invariance point? You have two, which is eutectic. Then awak kena tahu dia punya reaction je lah. L into alpha plus beta. And then peritectic, we have peritectic tadi, liquid plus alpha turning into gamma. Liquid plus alpha turning into liquid plus gamma turning into gamma. Gamma. Okay, so that's all about your chapter phase diagram. Okay, so these are the terminologies that you have. By now, you should be able to know already. Liquidus is the line of which all alloy is liquid. Above liquidus line is liquid. Solidus is below the solidus line will be solid. Solvus is the limit of solid. Invariant point ni is where three phases in equilibrium, three phases exist. Eutectic structure ni, it will result in alternating layers, or we call it as lamella. Pro-eutectic ni ataupun primary. Okay, it form before eutectic point. Okay. Okay, then terminal solid solution, it contain the pure components at the end of the phase diagram. Okay, contohnya macam alpha dengan gamma ni lah. That one is terminal solid solution, alpha and beta. Okay, pure alpha, pure beta. And then hypoeutectic ni having composition less than eutectic, belah kiri, left. And hypereutectic, composition greater than eutectic, ataupun right to your eutectic point. Okay, so that's all. So after this, you can do the exercise. Okay, thank you.